The velocity attained by the body when it reaches point Z, let it be Vc. When a spring is compressed or stretched, the spring force is given by the equation Fs equals minus Kx. In mechanics, we say that kinetic energy is lost due to the frictional force. Some amount of kinetic energy is lost due to frictional force. Hello students, welcome to this second session on chapter 5, Work, Energy and Power from first PUC Physics. I am Madhu R from the Department of Physics at Vidhyaashram PU College, Mysuru, your Temple of Excellence. In the previous session, we had a discussion regarding scalar product, all the properties and the operations that were performed in scalar products, what was work, the nature of work, which meant that what was positive work, what was negative work, when was work said to be zero, work done by a constant force, work done by a variable force, the work energy theorem, energy and its types. Okay, let us move on and have a look at the other concepts today. Let us begin our discussion from what is called as a conservative force. When is a force said to be conservative in nature? A force is said to be conservative if the work done by the force depends upon the initial and the final positions of the body. Where did the body start? Where did the body end? Okay, the initial and the final position. In a conservative force, the path traveled by the body does not come into picture. It is only the initial and the final positions. Okay, for example, gravitational force is always conservative in nature. Similarly, electrostatic force, spring forces are always conservative in nature. Then what is a non-conservative force? A force is said to be non-conservative if the work done by the force depends upon the path followed. Okay, this is the initial position, this is the final position. I don't bother about the position. Here, the path traveled by the body plays an important role. Okay, so the work done depends on what is the path traveled by the body. What are the examples? Frictional force is a typical example of a non-conservative force. The resistance offered by air when a body is freely falling, okay, that is also a non-conservative force. Similarly, the viscous force is also a non-conservative force. Let us check the differences between conservative and non-conservative force. It is of academic importance, could be a typical 3-mark question. What is a conservative force? Any force when the work done by that force depends on the initial and final positions. If the work done by the force depends on the initial and final positions, it is conservative. If the work done depends on the path followed, then it is non-conservative. Okay, because the positions depend here, work done in a closed path or a round trip is said to be zero. Okay, work done in a closed path or a round trip, if the path followed is like this or it is circular in nature, okay, work done is zero for a conservative force, whereas for a non-conservative force it is not zero because the path followed plays an important role. Work done is completely recoverable in case of a conservative force, whereas in non-conservative force it is not recoverable. Conservative force, it is central in nature, whereas the non-conservative force is retarding in nature. It is usually opposite to the direction of the work done. Okay, let us move on. What is conservation of mechanical energy? A very, very important concept. What does this mean, conservation of mechanical energy? The total mechanical energy of a system is conserved if the forces doing the work on it are conservative in nature, which means that the work done depends upon the initial position and the final position. Okay, then mechanical energy is conserved. Suppose a body undergoes a displacement dx. The body was here, it is moved by a distance dx. Okay, this distance is dx. Under the action of some conservative force, maybe spring, maybe gravitational, depends. From the work energy theorem, Kf minus Ki initial kinetic energy and final kinetic energy, the difference between those two, or you can simply say delta K. It is given by integral xi to xf fx of dx. Okay. The potential energy is defined by the force and it can be written as xi f of x dx for the difference in potential energy, delta V, Vi minus Vf. Okay. So from these equations, what can I infer? I can equate both, saying that Kf minus Ki equals Vi minus Vf, or Ki plus Vi equals Kf plus Vf. What can you understand from that equation? The initial mechanical energy of the system is equal to the final mechanical energy. Please remember, mechanical energy is a combination of kinetic energy and potential energy. Okay. This is kinetic, this is potential. Initial energies, this is kinetic, this is potential, final energies. Okay. So the initial mechanical energy of a system is equal to the final mechanical energy of the system, which in turn means that the mechanical energy is conserved. Okay. So conservation of mechanical energy effectively means that the initial energy is equal to the final energy. Okay. Let us try to get a proof of this. What is the proof? Suppose there is a body, okay, which is lifted up to a height h. There is a body at height h. Okay. The body is having a mass m. It is at position B. This body is at a position A at a height h. It falls down by some distance x and comes down to position B. Then it further falls down to the ground level, which is at C. Okay. So let us check. At point A, at this point, okay, consider a body having mass m. Okay. Because the body is at that point, the initial velocity is 0. I have not dropped it onto the ground yet. It is at a height h from the ground level. Okay. The kinetic energy is given by half mv square. V naught is 0, therefore kinetic energy is 0. Initial velocity is 0 because it is at rest at that point. Okay. What will be the potential energy? The potential energy is V is equal to m into g into h, because h is the height at which that object is placed. Total mechanical energy at point A is a combination of kinetic energy and potential energy. Kinetic energy is 0. Potential energy is mgh. So at point A, the total mechanical energy of the body is m into g into h. Okay, at point A. We need to check the total mechanical energy at point B and point C. Okay, let us now come to point B. What happens at point B? Let the body be allowed to fall from A to B. Okay, it reaches to point B traveling a distance with a velocity Vb. Okay. What is the distance traveled? The distance traveled is x. Okay. Then AB is equal to x. If AB is equal to x and the total distance is h, what is the distance between B and C? It is h minus x. Okay. The total height at point A was h. Between A and B, it has fallen down a distance of x. So the remaining distance is h minus x. What is the potential energy attained by the body at position B? It is given by V is equal to mg into h minus x. That is the potential energy. Let us check what is the kinetic energy. The velocity attained is given by Vb square equals V naught square plus 2gx. The initial velocity of the body was 0. So Vb square equals 2gx. Let us check the kinetic energy. The kinetic energy is given by half mv square. At point B, let the velocity be Vb square. I will substitute for Vb square from this equation. So kinetic energy is half into m into 2gx. This 2 and 2 gets cancelled. You are left with mgx. Okay. So what is the total mechanical energy at point B? At point B, the total mechanical energy is a combination of kinetic energy plus potential energy. Kinetic energy is mgx. Potential energy is mg into h minus x. If I expand, I get two expressions of mgx, one with positive sign, one with negative sign. They get cancelled. So at point B, the total mechanical energy is once again mgh. Please remember, at point A also it was mgh. Now let us check what is the total mechanical energy at point C. At point C, the body reaches the ground. Okay, it is at ground level. At height 0, the potential energy V is equal to m into g into h. H is 0, so total potential energy is 0. What should we take now? Let us check what is the kinetic energy. The velocity attained by the body when it reaches point C, let it be Vc. So Vc square equals V naught square plus 2gh. It has fallen down from A to C. So the total distance is h. We know that initial velocity was 0. So I am left with Vc square equals 2gh. What is the expression for kinetic energy? Half mv square. At point C, let the velocity be Vc. So substituting for Vc from this equation, I have half into m into 2gh. 2 and 2 gets cancelled. I am left with k is equal to mgh. At point C, the total mechanical energy is potential energy plus kinetic energy. Potential energy is 0. So the total mechanical energy is mgh. So from the three equations, what have we learned? That at point A, B and C, the total mechanical energy is mgh. Or it remains the same, or in other words, the mechanical energy is conserved. Okay. From equations 1, 2 and 3, it is clear that mechanical energy of a body during free fall under the action of gravity remains constant. It does not vary. Okay. Now, let us move on and check what is elastic potential energy. In the previous class, we had checked slightly about the gravitational potential energy. It is the energy possessed by the body due to its configuration or position. Let us have a look at the examples. A spring wound in the clock can possess elastic potential energy. A stretched bow, a bow and an arrow, can possess elastic potential energy. This elastic potential energy is the energy stored in the spring. It can be either when the spring is stretched or when the spring is compressed. It can be in both conditions. When it is stretched also, there is some amount of energy that is stored. When it is compressed also, some amount of elastic potential energy is stored. Typically, whenever we speak of elastic potential energy, the best example can be given is that of a spring, whether it is compressed or stretched. Let us check what is the spring force. When a spring is compressed or stretched, the spring force is given by the equation Fs equals minus Kx, where K is the spring constant. We have already studied this. This force law is called as Hooke's law. This was given by Hooke. The spring force is an example for a variable force which is conservative in nature. So how can I define this spring constant? Force constant or spring constant is the restoring force per unit displacement of the spring. If the spring is displaced by 1 unit, whatever is the force that is exerted, that is called as the spring constant. The unit for spring constant is Newton per meter. The dimensional formula is m L to the power 0 T to the power minus 2. Okay. K is given by F by X. Now let us prove that spring force is also conservative in nature. Work done by the spring force is given by W equals integral 0 to xm. Why have I taken this xm? Suppose this spring is stretched by a distance of xm. So from 0 to xm, that is the limit under which this integration can happen. F of s dx. We know that spring force equals minus kx. So you can also write it as minus kx into dx. If the spring is stretched from the initial displacement xi to the final displacement xf, then work done is given by minus k integral xi to xf x dx. We know that integral of x dx is equal to x square by 2. So what can I do? Instead of writing this, I can write it as w equals minus k x squared by 2 from xi to xf. So when I substitute for xf and xi in place of x, I get it as minus half k xf square minus xi square. If the spring is pulled from position xi and allowed to return back to the same position xi, okay, the spring is pulled from one position to a length and then it is allowed to come back, then what will happen? Replace this xf by xi, this entire term becomes 0, or simply the work done shall be 0, which means that the spring force is conserved, it is not going anywhere else. Now let us check the expression for potential energy of a spring. Okay, let us see. A spring is attached to a rigid body at one end and is attached to an object at the other end. Let the spring be stretched through a distance of xm, okay, using the force. Now let the spring be stretched through a displacement xm. Work done by the spring force is given by w equals integral 0 to xm f of s dx, where f of s is the spring force. Okay, we know that spring force is given by minus kx, where minus k is the spring constant. So I can write this as integral 0 to xm minus kx dx. Please note that k is a constant, so I can take this outwards. Work done equals minus k integral 0 to xm x dx. What do we know? Integral x dx is equal to x squared by 2. Okay, so upon integrating, I get this as minus k x squared by 2 from 0 to xm for the value of x. So I'll take this 2 also outside, minus half k xm square minus 0. I have substituted for x here, xm and 0. So I get it as xm square minus 0. Work done is minus half k xm square. The work done is stored as potential energy of the stretched spring. So potential energy V of x is given by minus half kx square. Please remember, the same shall also be true when the spring is compressed. Once we know the potential energy of the spring, we have to invariably check what is the kinetic energy. The total mechanical energy of the spring at any arbitrary point x, where x lies between minus xm to plus xm. Okay, this was the resting position 0. It can be stretched up to xm, or it can be compressed up to xm minus xm. So the limit is minus xm to plus xm. For such a case, the total mechanical energy is given by combination of potential energy and kinetic energy. Okay, kinetic energy is given by half xm square, and this is given by half kx square plus k is the kinetic energy. Okay, so I have k is equal to half into this small k is the spring constant. Please don't get confused between the two. This is kinetic energy, capital K. This small k is the spring constant. Okay, into xm square minus x square. For maximum speed of the spring, when x is 0, k max is given by half into k xm square, or v max shall be given by square root of k by m into xm square. Okay, this can be further used if required in the numericals. Now let us come to various forms of energy. Okay, we have been discussing only mechanical energy. Okay, in that we have been discussing potential energy and kinetic energy. What are the other forms of energy that are available? Let us have a look at them one by one. Okay, first and foremost, the heat or thermal energy. Okay, in mechanics we say that kinetic energy is lost due to the frictional force. Some amount of kinetic energy is lost due to frictional force. Okay, for example, the efficiency of an automobile is never 100% because there is some amount of energy lost in between the friction between the tire and the road. Okay, So that is what we are saying. Kinetic energy is lost in the form of friction. But the work done by the friction is not lost. Why? Because it gets converted as heat energy. If you may have observed, the tire gets heated up after you travel some distance because of the friction between the tire and the road. This raises the internal energy of the system. An object possesses heat energy due to the disorderly motion of the molecules inside the object. Because of the motion of the atoms and molecules inside the object, the internal energy is built up and thereby some amount of heat is produced. Okay, the best example is rubbing of your hands. The next type of energy is the chemical energy. Okay, chemical energy arises from the fact that the molecules participating in a chemical reaction have different binding energies. Okay, what is this binding energy? Chemical energy that is released during the chemical reaction is because of this binding energy. Okay, the protons and neutrons and electrons are binded to the atom because of this binding energy. If the total energy of the reactants is more than the product, heat is released. In some reactions, heat is released. This reaction is called exothermic reaction. What is the best example? Combustion of any fuel. You put some fire onto a wooden block, it gets ignited, gets combusted. Heat is liberated. Typical exothermic reaction. Typically, in our body also an exothermic reaction takes place, which is respiration. Okay. Then what is the opposite of this exothermic? If the total energy of the reactant is less than the product of the reaction, heat is absorbed by the reaction. This is called as endothermic reaction. You put some alcohol on your hand, you will feel that it is very cold. This is nothing but an endothermic reaction. Melting of ice is an endothermic reaction. Photosynthesis is an endothermic reaction. You can observe how heat is absorbed by ice, which is an endothermic reaction. During combustion of a fuel, heat is liberated. This is an exothermic reaction. Okay. Let us check the other forms of energy. The very famous form, which is the electrical form of energy. What is this? The flow of charges constitutes the electrical energy. Work is done to move the electric charge from one point to another in an electric field. The positive or negative charges have to move from one position to another position within an electric field. Okay, this work done will appear as electrical energy. One of the most famous form of energies, and typically the most upcoming form of energy, which is the nuclear energy. What is this nuclear energy? The energy required to hold the nucleons. What are nucleons? These are neutrons plus protons. Combination of neutrons plus protons, which is inside the nucleus of an atom, is called as nucleus, and the energy required to hold these within the nucleus is called nuclear energy. When lighter nuclei, the mass of such atoms are lighter in nature. When light nuclei combine or fuse together to form a relatively heavy nucleus, it is called as nuclear fusion. There is fusing of atoms, they come together. Okay. In this case, mass of the heavy nucleus shall be less than, please note, shall be less than the sum of the masses of the reactants. This mass difference is called mass defect. Okay. This reduction in mass is converted into energy according to the famous Einstein's equation, E is equal to mc square. In this case, we have taken it as delta m because that loss is very small. Energy is released in sun and all the stars by this fusion reaction. Okay. Combination of two lighter nuclei to form a larger nucleus. Okay. What is the opposite of this? When a less stable heavy nucleus like 92U235, the famous uranium isotope, okay, This is not stable in nature. It breaks up or splits up into two stable nuclei. This reaction is called nuclear fission. It is called as fission reaction. In this case, the final mass is less than the initial mass. Mass difference translates into energy. Whenever there is change in mass, it can be converted to energy. Whenever there is change in energy, it can be converted into mass. Okay? By the method of controlled nuclear fission, electricity can be generated. All our nuclear power stations does this effectively. Whenever we have an uncontrolled fission, it is nothing but a nuclear bomb. All the atom bombs and nuclear bombs are typically uncontrolled fission reactions. Okay? So by this we come to the end of this session. Have a wonderful learning experience. Thank you.